Welcome back, everybody. This is going to be the final of 3 parts in my series on the principles of counting. If you haven't watched the first 2 videos, please go and check them out now. In this video, we're going to talk about combinations. Let's get started. A combination is very similar to a permutation, except that order does not matter. This time, we use a C for combination, but we read this as N choose R, so P for pick, C for choose. By the way, you may also see it written this way as N on top of R in a big set of parentheses. And notice this is almost the same thing, except that I've got an extra R factorial in the denominator. Sorry, everybody. Technical difficulties in the middle of my sentence there. I was about to say, let's try a quick example of actually computing a combination. And let's compute 10 choose 4. Well, according to the formula, by the way, this would be the same thing as 10 choose 4 written this way. And that's the number on the left, goes up top. So I get 10 factorial over R, which is the number to the right, factorial. Oh, excuse me, in this case, that's 4 times 10 minus 4 factorial. So we have 10 factorial over 4 factorial times 6 factorial. Let's expand this out just a little bit. I need to make myself some more room. So on the top, we'll get 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Not that the 1 super matters. On the bottom, we've got, from the 4 factorial, 4 times 3 times 2 times 1. And then from the 6 factorial, we've got 6 times 5 times 4 times 3 times 2 times 1. And now we've got a bunch of stuff to cancel. Notice all of my factors 6 and below cancel with my 6 factorial on bottom. Now, though, I've got an 8, which cancels with 4 and 2 down here. And I can cancel one factor of 3 here. And everything on the bottom is now just 1. And I'm left over with 10 times 3, the 8 is gone, times 7, the rest is gone. So this is 210. Notice we got a lot fewer combinations than permutations in this example. And that's because if the order didn't matter here, if I could elect, or if the roles didn't really mean anything, I was just electing any 4 people, then if I take 4 people and look at all the different ways that I can give them the labels, that adds a lot more things to count than just the 4 people. So we should expect to have fewer combinations than permutations. Let's do another example. How many 5-card hands can be dealt from a standard 52-card deck? In a standard deck, there are no cards that are repeated. So how many combinations of 5 from 52 can I make? Go ahead and pause the video here to see if you can tackle it on your own. I found that there are 2.5 million ways to deal a standard 5-card hand out of a 52-card deck. Here's how I got that answer. I want to show you a quick simplification trick that I use with these problems, because writing out all 52, 51, 50, 49, 48, 47, 46, 45, and so on gets really exhausting. When I already know once I hit 47, I've just got 47, 46, 45, 44, 43, and so on left, or I've got a 47 factorial left. So I just stripped out the first 5 terms, which left me over with 47 factorial, and that cancels with my 47 factorial on bottom. What I had left over to work with was these 5 numbers on top and these 4 numbers on bottom. My 5 and 2 make 10, which cancels with a factor of 10 and 50, leaves me over with 5. 4 and 3 make 12. Which 48 has a factor of 12, and I'm left over with 4. So all in all, I get 52 times 51 times 5 times 49 times 4, which gives me 2,598,960 ways. That's going to wrap it up for this video and this lecture series, where we saw the principles of counting, permutations, and combinations. Catch y'all in the next one.